too near, or actually hitting the German ship. With this computer, if you put in enough parameters about the speed and direction of your ship, the speed and direction of the enemy ship, and perhaps a little bit about the winds and tides, but obviously if the tides are very, very high, there's some variability there. The machine, quite quickly, was able to do what the calculations were quite significant in terms of rocketry, because the shell goes up and down in the shape of a parabola. So you need to understand a little bit about maths. Once that's programmed into the machine, time and time again, you can get it right quickly, and we were hitting the Germans dead on.
First time.
First time, or at worst, second or third time. But we were getting there. And once you've got the range, you can then tell all the frigates and all the destroyers and all the other ships, this is where they are, this is how far you need to go, 270 degrees, 8,000 yards, start firing that way. And they all work it out. The machine was therefore beginning to save lives. And towards the end of the war, about late 1943, there was an awful lot of V1 rockets coming overhead into London. And tens of thousands of people per month were losing their lives. The country was getting demoralised. Hitler had found a weapon that the British couldn't stop. No plane could travel until the Meteor was invented as fast as a V1 rocket. This rocket would go overhead in the shape of a parabola. And if certain observers looked at one part of London, the angle with which this rocket was coming down to land, and another part of London, and they noticed the shape, the angle with which the V1 came down, and the direction, they could back triangulate and find out where these rockets were being launched from, and I keep forgetting the name of the place. Peenemünde. The Allies were then able to find the source of these V1 rockets that they'd not been able to find before, and bomb the living daylights out of it, save tens and tens of thousands of lives. So this machine with the funny little wheels next door, which we're just about to go and see, was actually responsible for saving lives. Not this actual one, because this is a replica, but machines like it. So these are real world problems.
Yeah, we've spoken quite a lot, and I realise it's a lot of information to take in. And the idea is to give you tastes of the Meccano part of it, what changed with Meccano, the machine itself, the equations. So we're going to go and show you some equations on the machine now. There are some other books in there as well, which are incredible, incredible books. There's an original Babbage in there, which when Matt saw it, he actually squealed. It's amazing. But there's some posts outside, and we'll all be floating around. So if you have any questions about any of it, please come and find us. I would say go and watch the machine initially, because you'll be fascinated by how it works. But apologies for talking so much, because I know you're actually in that part of this. But please follow Matt and Ian through, and they will help you now. Show you, sorry.
If anybody's got any questions, that's what we want. No questions too silly or stupid.
Go and see the machine.
We don't want to blind you with science. It is actually quite simple in the way that it does it.
Yeah, thank you.
How many words? I think it's basically one of the...
These ones. Every conference I go to, I bring the toys. Yes!
This is Josh. Josh, the thing that you have to see is next door. What? No, it's one of the other things that we're doing.
It's a real thing there that was actually used when Hartree and Porter were trying to devise a system for doing these computations. Now, the mathematics that it's doing is merely integrating. It's merely finding out the area under a graph. So you've got, say, a reasonably odd graph here, and I've on purposely made it curved. It's not straight lines. Anybody with a protractor could add up the area under a graph and come up with some kind of mathematical relationship. But when you start to introduce curves, and these are real world curves because nature has gusts in the wind, the curvature of the earth is a factor when the weather is changing, you need a higher level of maths. And this machine simplified that. The principle that it works on is to measure the speed at one point on this disk. And Ian, can I get you to kind of explain what's happening as one of these disks rotates? What's happening after that?
Yes, basically the input into the disk is through some threaded rod, and it actually displaces the centre of the disk away from the wheel. So at the
So
very
this little wheel here is going to pick up
yes.
the rotational speed on the outside. So it's at right angles to this disc here.
So as it moves, you can,
So
it's
the
in the
disc will
centre,
rotate.
and at the centre it won't rotate, but as you put in the graph there, you're actually displacing the machine, and you can just see the wheel starting to move. So when it's very, very near the centre, the wheel will be going around very, very slowly, but then as I increase the distance, the wheel will start going around faster and faster and faster. And that is not a straight line sort of function or whatever. And this really is the key to the whole thing. So what actually happens is that you have a motor that is continually driving these discs round at a constant speed. At the same time, these tables are being moved. This is the function, what we're trying to input to measure the area under the graph, and this is the output, and that pen will actually plot an output. This motor, as well as driving the discs, is gradually moving that table along. Here you have a set of crosswires. So the idea is that as the table moves and the curve increases, you try and follow the curve by keeping the crosswires over the curve. And as you can see, as I'm following it, the wheel will get further and further away from the centre, and the faster and faster and faster it will go. So that is how you input everything. But the problem is that because this is glass and because this is metal, it's really easy for the wheel to slip. If it slips, then the calculation is null and void. But the problem is, we now need to drive the pen and the plotter. And it just wouldn't work normally, because it would just keep slipping. So then we've introduced this item here, which is the torque amplifier. This is the input, and the input shaft just goes onto that arm. This output shaft is separate, it's just located in there just to keep the whole thing level.
So you've got two shafts, one here and one here. So there's an input shaft and an output shaft in between the two. Go on in.
Yep. And on the input shaft, there is an arm. On the output shaft, there is an arm. And what you do is to wrap cords around these drums in opposite directions. These drums are free to rotate on that rod. So if you spin these drums in opposite directions, then everything is in equilibrium. Nothing moves.
And the bands are wrapped in opposite directions.
In opposite directions to keep the whole thing in equilibrium. So then, if I put a very small bit of movement on here, and these things are spinning, the bands will start tightening up. And through that, they will amplify the torque maybe 80 or 100 times. But they won't alter the speed of the shafts, even though they're running around at 100 RPM, or reps per minute, because the whole lot is in equilibrium.
Let me just step in there then. So what Ian's got here is this thing very similar to power steering on a car, for instance. So if you if your power steering wasn't operating, and if you've ever turned your engine off on your car and you've got power steering, when you try and wrench that steering wheel around, has anybody gone into a car parking space, stalled the car, and you didn't realise that you stalled the car, and you're pulling the steering, and you really have to wrench on that steering wheel, right? Has anybody done that?
My driver Morris Marbury doesn't have.
Well, there you go. So you must have quite strong arms. So if you're driving a truck, it probably is almost impossible to steer a truck unless you've got power steering. So what this device is doing is taking a small amount of torsional force, torque, and anybody with power steering actually working while the engine's running could probably put your little finger on that steering wheel and turn the steering, and you are turning the front wheels with absolutely no difficulty whatsoever. And that's all this thing is doing. It's taking your little finger to move the steering wheel so that the steering wheels, or some amount of something, is being changed significantly. There's a significant amount of force needed to move those wheels. So it's helping you do the job. Because of this slip that Ian's mentioned here, there's a risk of slip, and that's going to introduce an inaccuracy. We'll talk about inaccuracy in a minute. But finally, after here, we can then drive almost any part of the machine. What we're going to do now is to operate just this part of the machine and the input and output tables. You've got another part of the machine that we can use later, and in fact we can use more and more and more and more, and add up and make this rather a large machine, so it can actually be solving equations which have a significant number of terms. And Tom, just remind me, how many terms Van der Bush's machine? Was it 18?
18 integrators.
He had 18 tables lined up. So the number of terms in his tables made that he could solve incredibly complex equations. Not all of the outputs from the tables need to contribute to the output equally. So Ian's got a gearbox here. Please go on.
Yes, basically this side of it is the program, and this is my programming tool. Because you physically have to attach one shaft to another shaft. You have to get the shafts rotating in the right direction. So there are reversing gears here. So if I wanted that shaft here to go in the opposite direction, I could then engage with that gear there, because two gears mesh with each other, they turn in opposite directions.
So we've got a term in the mathematics that is either added to or subtracted from. You've probably seen the equation at school. If you've got A plus B, well here you could move this over and do A minus B.
So the actual direction is plus or minus, and the sort of speed of it really is the output of your equation. At the moment, as I said earlier, when you wind this handle in, it displaces the disc, taking the wheel further and further and further away. Then through the torque amplifier, it comes through this right angle gearing here, through here, all the way down here, and drives the shaft here, which actually drives the pen in that direction. But at the same time, this table will actually be slowly moving. So in the end, you'll see a graph being plotted of the distance travelled. Now, I have got a mechanical counter here, which I shall zero, and that is counting the number of rotations of the shaft, and that will actually give a numerical output saying this is what the area is. And this will be your total distance travelled. And it will say it'll be 2 miles or 21 miles or whatever. So that is like your digital output. So that roughly is about...
Yeah, so let's pick up that example that I was talking about, the car driving down the street. This kind of calculation is being done by your sat-nav continuously. For instance, if you're stuck in traffic and you have to slow down, then your sat-nav will tell you that your estimated time of arrival is actually a little bit later than it was. If you turn off a road and think, oh, I've got a shortcut here, sat-nav hasn't told me to go this, no, I'll just nip off there and get round that traffic and I'll go over there. It then has to recalculate how long it's going to take and how far you're going to travel. It's having to do this kind of maths all the time. And if you've ever seen your sat-nav hesitate when you turn off, it's not just because it hasn't realised that you've turned off. The satellite navigation system knows immediately that you've turned off that main road. It's having to do some recalculation. So it'll take a second or two before it suddenly says, oh yes, I know where we're going, okay, we'll go that way, we set up a different route, and by the way, you're going to get there 10 minutes early. So that bit of digital electronics in your sat-nav is having to do exactly what this machine is capable of doing. We've got a trivial example. We're talking about a car driving down the street, a simple understanding of the distance travelled because the car's doing speed. Once you start to add extra sections of machines, you can then look at things like gravity, you can look at all manner of economic factors, population growth, huge amounts of mathematics that then become open to you to, for instance, ballistics in the Second World War. We can then actually back calculate where those V1 rockets are coming from, because we've got some extra terms here we can understand about this parabola, and we can actually stop the Germans from killing people in London. And that's the beauty of this. It's actually relatively simple. In, out, and out it pops. Let's do it.
Yeah, you ready?
So I'm going to follow the graph here, and I think you guys can have a guess as to what shape of graph this might come out. I'm going to talk you through us setting off down the street, and you'll be able to see on here. I hope, if anybody can't see, would you make room for others to move around? We can actually stop the machine in mid-calculation. It doesn't forget.
No.
So if you do need to move around, this kind of machine doesn't mind being interrupted. Just because we haven't put 50p in the meter, we can pick up where it left off. So Ian, fire away. Let's do this.
That's what